I did my dissertation research on something called distributed hash tables, which are these data structures we're looking at, only the data is distributed amongst an entire network, right? And they're these kind of really robust data structures and networks. So, all right, so let's take a look at a famous one, SHA-1, right? Okay, so, or actually possibly, better yet, Md5, right? Md5 Hash Generator, great, right? So the idea here between the hash function is that you take you give it any kind of data you want, right? And it will generate some string of digits. Specifically, Md5 creates a 128-bit fingerprint for it, basically 128 bits of information that says, if you give me this same exact file, I'll always give you the same 128-bit sequence. So if I say hello world, right, it's going to generate this string for hello world, right? Typically, you don't give it a tiny, tiny string, though. Typically, you give it like a 4 gigabyte file or something, and it just goes through it and chugs through it and is able to spit out a basically a unique identifier for it, okay, based on the binary data. So if I change, and here's the big thing about hash functions, or at least these secure hash functions. If I change it just a little bit by adding a comma, right, to hello world, we get a fantastically different, so that was E4D7 now, and E4D7 is what we got, and if we do, and instead here, we get 5EB6, right? And again, this is in hexadecimal. So these things are very different, but if I do hello world again, it's going to give me the exact same thing if I put in the exact same thing. Java has a function called hash.hashcode built into it, so you don't have to think about this or create a good one, because creating good ones that result in very few collisions, right? Making sure that everybody gets their own parking spot and the parking spots are equally distributed throughout the entire parking deck. That's actually a really tough challenge, right? It's easy for you to build a bad hashing function. For instance, my bad hashing function is I say everybody should go park at spot 0, right? But that means that we get a collision each time. And so, okay, the first person gets there, they get to park in constant time. But the second person, they have to look one over. The third person has to look another over, and so on and so forth. So it ends up being an O(n) algorithm. So bad hashing functions are easy to create. Great ones aren't. So what do we use these things for besides that? One thing we use hashing functions for is making sure our files that we download are what actually we were told we were going to download. Okay, so for here, kind of the idea is if I go to download, Ubuntu 18.4 long-term service, right? Right, I could download it, and let's see, verify your download, right? And you can use SHA-256 to do that. So let's see, it tells you just all versions of Linux. Yeah, so I could just simply do, so verify the SHA-256. I can say, hey, verify these fingerprints and stuff, right? And that's part of it. Right, so I could just basically check this number without having to check these numbers without having to check anything else online. So I could verify that what I download was actually what I download. And actually, Linux Mint, a very popular version of Linux, actually ran into trouble a number of years ago because somebody managed to get on their website, okay, and here if they on their download page, right, they managed to basically upload an altered version of the disk file, basically the thing you'd use to install the operating systems, and then they also managed to change the SHA-256 thing. So here, right, if you download it, you should be able to run SHA-256 sum, which is a small program, and get the SHA-256. So SHA, by the way, is another hashing algorithm. It stands for Secure Hashing Algorithm. Any guesses as to what 256 stands for? 256 bits, right? The bigger the more bits you have, by the way, the harder it is to to basically fake, right? So they were able to alter it, and they either hacked this file too, or they got it so that the ISO had the same key as the they were able to switch up the bit so we would get the same SHA. And it's not impossible. It just takes a lot of time to do that. So the entire point of these hashing algorithms, though, for us is to figure out, hey, if I've got this giant array, where am I going to put a particular item in this array? And if I can use this algorithm and everything maps to its own unique space, or if I am able to map it to something that's close to it, then I can do constant time lookups, right? So these are extremely powerful tools that we use, and specifically we use these to build hash sets and hash maps, which are going to be used for your homework. This project. Now this one, as I consider really important, as you may have noticed, it is worth not 1 but 200 points. Okay, so this one is, and it's due sometime late next week. Okay, but first let's go over the data structures that we will be covering. So the hash set is one of those that you really wanted but didn't know you needed, right? Remember from all the way back to our second week, the first problem was checking to see if everything checking if everything in the list was unique, right? Everybody remember that one, right? How long did it take you to write? What was the big O time that you managed to write? O of n squared, right? For every item, you had to check it against every other item, right? Hash sets exist to basically make sure we can do that much quicker. They are essentially checklists. Okay? They are nice big checklists. Mainly, I can add stuff to a set and then I can check if it's already been in the set. These sets act exactly like mathematical sets. So if you've done your set theory from Math Concepts 1, right, then you know exactly how this works. If you've taken Math Concepts 1, right, and you ran into sets there, then you know exactly how these data structures work. They just don't use the same names. They don't use union or intersection. They use something like add all. They use add all and retain all. So anyway, let's go ahead and take a look at a file on how to do that. So new file, new data structures, new Java class, unique with sets. All right, unique with sets. Public static void main. Okay, and now let's take a look at how to use this. So we want to public static boolean all unique list list. So basically what we want to do, right, if you remember this one, is that we are checking to make sure we're checking to see if everything in this list is unique. So I'm going to just go return true. Now let's go ahead and see how we can use a hash set to do this. So the way we do that is a set is the abstract data type, just like a list is, right? There's many ways you can implement a set. But the two main types are hash set, which uses uses constant time, add and remove, and the other way is tree set, which uses log n, add and remove, because it uses a binary search tree. Now, why would you want to use that? Because of the other cost, right? I mentioned there were two things we sacrifice. two prices to pay for the power of constant time. The first is that we waste space. The second is that we cannot maintain any semblance of order inside our hash table, right? We can't iterate through from smallest to largest. The best we could do is print out everything and then sort it, right? Whereas a tree, everything's kept sorted. So, So here we would use set E. Set is equal to new hash set. There we go, hash set. And that creates a new empty hash set for us. No worries. Okay, and now for E item in list, what we're going to do is that we're going to say if set dot contains item, right? Now, because we're using a hash set, believe it or not, this doesn't take O of n time. This takes constant time because we're using a hash set. Hash sets are magic. It's able to basically look up and say, hey, where in the parking deck is this item, right? And just use that magic hash formula to figure out, okay, if we've added it, it would be here. If it's not here or somewhere nearby it, and it knows to stop searching for it, by the way, when it hits an empty space, right, is kind of the idea, right? If you're looking for your car, right, if you're trying to say, hey, if you're looking for somebody's car, like maybe your brother's or something that was parked in that parking deck, you know his license plate number, you go to the space, you check, okay, somebody else is parked there, somebody's parked in the next space, there's no car in the next space. If your brother had parked his car, it would be in that space, but he hasn't parked his car, so it's not there, right, so you can stop searching. So it knows how to search, so we can check if it contains in constant time. And again, I explained this all in the videos. Okay, if the set contains item, then return false, right? Because if we already have that item, then all the items weren't unique. Else, set.add item. And that's it. That's all you have to do. You just have to add every item to the set. But if the set contains, and it's the same, you've already added that item to the set. If it contains it, then great. Also, that add is constant time. So for each item, what are we doing? We're doing a constant time add and a constant time contains for each item, which means, and we do that for n items, which means this takes O of n time. So it's an O of n algorithm, much, much quicker than what we had been able to do earlier in the semester. All right? So we can actually shorten this using the fact that, remember that there was all this confusion at the beginning of the class is like, why does the add method return true or false? Well, it's because sets will return true or false. They won't always return true here. So I'm going to change this and then I'm going to explain it. So if set dot add item equals false, return false. And that actually shortens that up even more. So here, what we do is that we try to add the item to a set. But remember, how many copies can a mathematical set contain of an item? Just one. Well, technically you can have like infinite, but it all reduces back down to the one, right? Right? There's no difference between A, B, C, and A, B, C in terms of mathematical sets, right? But here in computer science, we enforce that you can only have one copy of anything in a set at a time. So if it's already in there, we can't add it, so we return false from add. So add will return false. If we can add the item and it goes in properly, because there's not a copy over there, we just return true like we normally would. So if this fails, if set.add fails and returns false, then we return false because it has a duplicate in it. Make sense? So sets are pretty much useful for checklists, right? Basically, have I seen this item yet? That's the big use case for sets. Anytime you might need to do a mathematical set operation, that's when they're good for it too. But here we're just saying, have I seen this item? being able to constantly say, hey, have I seen this item, and checking for duplicates. That's your use case most of the time for sets. Okay. Now, hash maps are a bit more tricky. Okay. Hash maps are extremely powerful because they don't store, because here, hash map isn't going to be storing, it's not going to be storing one data item. It's going to be storing two. So let's take a look at a problem that you've probably come across that was pretty tricky. Public static public static car most common character string text. So here, the goal of this method is to return the most common character in a string, the one that appears the most, right? It's not like just finding the biggest number, right? Finding the biggest number, you just have to pass through it. But here, we have to keep track of the counts of every single character, right? Because that can change. Most common character. And so for here, we're going to, now, the typical way you do this before you know about hash maps is that you remember, oh, everything has an ASCII value, every character has an ASCII value, so we create an array that's 128 long, that's 128 characters long, character array 128 long, and we then translate every character, we put every character into its Unicode spot, or its ASCII spot, right, and then count them up that way. And that's kind of tedious. Instead, we're going to use a hash maps. Now, hash maps have three primary uses. The first is for literal key-value pairing, like a simplified database. Like, given your email address, I'm going to be able to find all your customer information, right? So I enter in your email address on a site that you shop at, right? And it then returns your shopping cart and all your other account information, right? It uses some kind of key, which is a unique identifier. That's typically your email address because it's not your address, physical address, because multiple people can live at the same address, right? So that wouldn't be unique. It's not your name because your name isn't unique. Also, some people don't have names that conform to the standard American first, middle, last, right? So that's not unique, and that's a whole can of worms. So we use your email address, right, or your account username, because that is, if you have to make one, as the key for your data. So that's one thing. The other two things that we're going to focus on with the homework as the other two use cases for sets. So the first one is counting things. For each of these things, I need to come up with a count for them. And the other thing is categorization, categorizing. So for a specific category, here is the list of things that belong to that category. And those are the two things we're going to use with that homework. So the counting is actually fairly easy to understand. So I'm going to create a map, and it's going to take in two generic things, not one. The first is the key. The key here is the character, right? That's the type. And then we're going to need to, and the value is an integer. So we're mapping a character to an integer. And that simply means that we are taking a look at every single character in this thing, and we're going to be looking at like the count of the character, right? We're going to be storing how many items, what its count is. So car count. And I ease into this a bit more gently in our videos, but I figure some of you might want to get started. So new hash map. I cannot stress enough how powerful this data structure is, to the point where basically big companies, when they do the whiteboard interviews, have to look it is very, very, very hard to find a question they'll ask you that you can't use a hash map on to make your job a lot easier. Hash maps are just that powerful. Okay, so let's go ahead and count each of these characters to find out which one is the most common. So standard thing. I'm going to just use a for each loop again. For car C in text dot to character array. Okay, so for every character in the string. Okay, because it's just easier to do a for each loop that way. So for every character C, this turns the string into an array of characters, so I can treat everything as an individual character. Right. Now, what I've got to do is that I've got to count up all the characters. So first thing I do is I ask if car count dot contains key C. And I'm going to put a not there, right? So if not car count dot contains C. In other words, what that translates to, have I added this character C to the map yet? Do I have a running count for this character yet? Okay? Am I keeping track of this character yet? If this is the first time I've seen it, then guess how many times have I seen it? One. So that's what I'll do. I'm going to do car count dot put. So that's the add operation for a map. Dot put character M1. That means now I put in the character C as my key, and it has a value of 1. Which means now whenever I need to ask, what I could do is that anytime I want to ask, hey, how many times have I seen the letter A? It would now be able to say, here's the amount of times you've seen the number of A. So given A, it would return, if I've seen A 5 times, I could then ask that character count, how many times have you seen A? Which we use with, and the way we would do that is character count dot get the letter I want the count for. And it would return not the letter, but not the key, but the value, the number of times I've seen it. So if I haven't seen it yet, I put it into the character count. Okay. Otherwise, if I haven't seen, if this doesn't fire, right, then that means I have seen it, right? It's in there. I've stored it in my hash map at this point, right? If the if statement doesn't fire, that means the else statement will, right? That means I have seen it. So what I'm going to do is that I'm going to get the count, number of times I've currently seen it, is equal to car count dot get C. So what I'm going to do is that I'm going to get the number of times I've seen this, right? Character. Int. The next thing I'm going to do is I am going to go ahead and then, well, I've seen it one more time, so what I'll do is I'll do character count dot put C and count plus 1. So all I've done is I've retrieved the value that was in there, right, and added 1 to it, and I'm putting it back in, right? So now that's all I have to do to keep track of all the characters, right? I don't do character count get dot plus plus because that wouldn't change the thing in there, right? Instead, I've got to, I get it, I increment it by 1, and there's nothing stopping me from putting this inside here, right, except for readability's sake. Okay. So now we've got a character count. So what we'll do is that we'll go and get and find the biggest. So that's a bit trickier. So for character C so I need 2 variables. Actually, I just need one. Biggest letter. Or most common. Most common is equal to, let's just go ahead and say A. I'm going to use tilde because that seems very uncommon, right? Okay. Character most common, and then let's go ahead and count is equal to, int count. In other words, the number of times I've seen it, it's going to be equal to -1, right? So anything that I've seen, right? So I've seen anything in here more than -1 times, right? So that's just simply so I can initialize these things, right? So now for every character in the map, and the way I do that is to iterate through that is I go, we call our map the character count, and we do dot key set, which will return a set, right? The thing we did, data structure we just talked about. It will return a set of just the keys. So for every key in there, so for every key that exists, what are we going to do? We're going to, I'm going to call this most count, right? Okay, sorry. I'm going to change that to most count just because that's going to make the most sense. So if if car count dot get C is greater than most count. In other words, I'm going to car count dot get C, that gets the number of times I've seen C, that gets the value associated with the key C. And if that is greater than the current, winner, right? If that's greater than the current thing I've seen, then guess what? Most common is equal to C, and most count is equal to car count dot car count. Oh, sorry. Yeah, car count. Sorry, lost my train of thought there. Dot get C. There we go. And return C. Return most common now. Right? Because that will be the most common character. Some variation of this question has been on your second exam. Last time it was just simply get a count of all the characters, right? Given a string, give me a count of all the characters. That was the question last year, which would just simply have been this code plus the return character count. Instead, it would return to hash map instead. That's always been a question on your next exam. By the way, when's your next exam? Next week. So we will be doing that, and I think for that exam, rather than having it separated to do in labs, it will be done in here. I'll do it in here, and I'll make the exam shorter because, you'll have an hour and 20 to do it. So it will be on next Wednesday. So you'll have a practice exam hopefully by tonight, okay? Now, what is the contents of the exam? Let me go ahead and show you the practice exam from last semester, okay? So the practice exam, and then once we go through this, I'm gonna go over the homework, and I'll let you guys get to work, okay? So classroom, teaching, right? Destruct. Exam to practice right over here, okay? So I give you a big exam, but that's just because there's going to be a lot. So it's going to look very intimidating in the length. It's not actually that intimidating because guess what? I just give you a lot of space to answer a lot of the questions. Okay. So your first page will be for each of the following questions, indicate which data structure would be best suited to handle each scenario. Use an array list, a linked list, a stack, queue, tree, priority queue, set, and map. And I will go over this I will go over the copy of the exam I give you on next Monday, right? So your exam will be Wednesday. We'll do a practice set. I'll do a practice exam overview on Monday, okay? Right, and so it just simply gives you a scenario and asks you which one's the one to do. Tree relationships. So the node at the top of the tree is called what? The links from a node to a successor are called what? Nodes that have the same parents are what, right? So those kind of things. So know your tree. But these questions will actually be a lot more like the quiz on relationships that you took earlier, right? In fact, the questions that I gave you on that quiz were actually the exam questions from last year. So that should give you a good example, and that's 10 points. Draw an example of each of the following types of binary trees. Use a different example for each of the trees. Right, so please draw me a full tree Please draw me a complete tree. Please draw me a perfect tree. I don't care about what numbers go into them. I just care is the structure, right? Because binary trees don't care about the contents. Binary search trees do. This one is always on the exam, just we always change the numbers, right? So this is on the practice exam and on the exam. We just change the numbers around. Draw the binary search tree that you'd get after you insert the following: 42, right? So that would be the root. Then you'd insert 10, which would go to the left of 42. Then you'd insert 50, which would go to the right of 42, right? And you just simply draw that tree, right? Make sense? Use your previous answer, and I love doing that. Use your previous answer to do the following. Draw what happens when you remove, right? So given your tree from last question, draw what happens when you remove that. Because I don't want you to cross-contaminate a wrong answer, although nobody gets that question wrong. I think I've had one person get it wrong over the past 3 semesters. So, and then it was just simply one person I've had one person who had it completely wrong because they didn't know what they were doing. And then I've had like 3 people over the past 3 semesters get some point taken off because they read like 50 and they accidentally put 15, so something like that. Right, minor stuff that's super easy to say. Stress of an exam, no worries. Right. So using your previous answer, draw what happens when you remove. So know how your add and remove work and be able to draw that on paper. Know your pre-orders and your post-order traversals of a tree. Right, all stuff that we've gone over. Know your heaps. So same question for heaps as for a tree. Build a min heap by adding items like we did that day in class, and I've got to grade those, which I plan on doing today. Using the heap, remove, right? So this is a lot of drawing, right? Not a lot of coding so far. And Huffman coding, right? Just like we did in class. Do Huffman coding. Draw the Huffman coding, and you'll get it. Here's the symbols. Here's the frequency as it appears. Draw the Huffman trees for these symbols, and then encode the string apple into binary using this encoding. And then you will have some coding questions, but not too many, right? And they'll be about this part. So coding, using a method given the root of a tree or subtree, computes and returns the number of nodes, right, in that tree or subtree. You may not use the size method. Forget that the size method even exists. Right, but I want you to basically count, and that will, basically this will test. Do you know how to do those recursive algorithms using a tree? Right, the type that I kept talking about in the videos. So if you haven't read that, gone over the videos, then, but this one, right, and so remember, for this one, it's fairly straightforward, but I'm not going to tell you yet because you probably want to work on it. I also like being able to write questions that ask you about the structure of a tree, right? Given a method of a tree, given a tree returns whether or not the tree is a full tree. So it's slightly different than those traversal methods you've tried so far because, but it still kind of follows the same thing, right? You'd want to check if it's a full tree, I first have to check, do I qualify as full? And if so, then I have to check if my left subtree qualifies as a full tree and my right subtree qualifies as a full subtree, right? Right, so there's the kind of recursion that would go on there. And then I give you extra practice, right? So here, notice it's 0 points, right? This one is just an extra question just that wouldn't be on the exam. It's a bit harder than what would be on the exam. But I wanted to give you some more practice because people ask it. Check if 2 binary search trees are equal. In other words, do they have the same items in the exact same structure? And then here is another question, and then here's the kind of question you would get for a map. Write a method that returns the characters that occur in a string and how many each times occur. So in other words, a shorter version of literally what we just did here in class. So another practice question. Write a method that, given an array of integers, categorizes them into numbers divisible by 2, 3, and 5. So if your input's like this, then we say here are the numbers divisible by 2, here are the numbers divisible by 3, and the numbers divisible by 5. That categorization is what you'll be using a lot in the homework. Then basic analysis questions. What are collisions? So long as you watch the videos for hash tables, you're going to do just fine on this. Okay, and so long as you do the homework or start working on the homework, you'll just do fine on it. Okay. So yes. Yes, you get to bring in a cheat sheet, of course. Yeah, you get to bring in a cheat sheet front and back, of course. You are allowed one sheet of notes front and back. So it's right over here. And who am I to fight with a PDF, right? All right, so let's go ahead and talk about your homework for the week, which is worth 200 points. So it's worth twice as much as regular homework. And this is the one homework that I exclude from being dropped, right? I will drop your lowest homework grade, but this is the one I don't drop. Okay, I actually have that programmed in. So, and this is one that I do encourage you to work in pairs, and you can demo as a pair, right? So, let's go ahead and take a look at it. So this is called Cheater's Hangman, and I totally stole it from somebody else, but that's okay because I totally put him in the author field, right? Right. So I stole this. A lot of his original explanations are in here, but I totally adapted this to be my wording. So Hangman is a game that relies on trust, right? That's kind of the idea here, right? Hangman relies on trust. In other words, it relies on us trusting, right? If I have a word up there, the trust that we rely on is that I'm not a cheating bastard, okay? So and how could I cheat in Hangman? And the answer is I could change the word that I was thinking of right from under you, and I'd have to be really petty to do that because I mean, who cheats at Hangman? It's just a game. Like maybe there's a pro Hangman league for like hundreds of dollars that I don't know about, but you know. All right. The core assumption is that we do not change the hidden word, right? So suppose we've made a lot of guesses and and this is what's been revealed, right? G-O-A, okay? We've already guessed T, so we know it's not goat, okay? We have one wrong guess left before we lose. So if we get this guess wrong, we lose. And based on our knowledge of the English language, there's only two more words that could possibly fit, right? Because we've already guessed goat, right? There's goad, where like I goad you into taking a rash action, or goal, you know. Everybody throws up their hand and go, goal, right? So anyway, in the normal games of Hangman, right, I basically could guess 50-50, right? You could guess 50-50 and I'd say, you guessed L? That's right. Goal is the word. Oh, you guessed D? No, I was thinking of gold, right? It's 50-50 shot, essentially, right? Ignoring like word frequencies there, or letter frequencies, right? Goal's more common than goad, right? Right? You got basically a 50-50 shot of winning, 50-50 shot of losing. However, if I am mean and petty, you guess L, and I say, oh, I'm so sorry, I was thinking of goad. And if you guess D, I go, oh, I'm so sorry, I'm thinking of L. That's what your assignment is, to make the pettiest game of Hangman that has ever existed. Okay, the idea here is that our computer is going to be a cheating bastard. Okay, now how do we do this? Basically, we kind of operate on we take advantage of the fact that your computer can keep track of all the impossible words in the English language and store them, you know, with no problem whatsoever, and process them like that, right? Your computer, you know, remember, in your pocket contains a supercomputer that is more powerful than the stuff we use to get to the moon, right? Your phone is more, and that was true for even a decade ago, 2 decades ago. Those phones are powerful, right? They can process stuff really quickly, right? Yeah, we have a dictionary, unlimited time, right, because it's super quick, and a galling, tragic, yet hilarious lack of morals, okay? So what we're going to do is that we are going to just simply, rather than, you know, choosing and sticking with a hidden word, right, we're playing Hangman, let's assume it's 4-letter words that they're guessing of. Rather than choosing or sticking to a single hidden word, we're going to make a list of all 4-letter words, and because some of those are not appropriate in an academic setting, we'll just simply limit ourselves and pretend the English only has these 7 words in the English language that are 4 letters long, right? Which are this team, look good, eggs, echo, and edge, right? Obviously there are more, but for the sake of our example here, I don't want to be having pages of stuff to process through right over here. Okay, so we basically take all those, so we parse our file, we grab all the 4-letter words. Okay, maybe you're smart and you store all the words in a hash map, so here's a perfect example of how to use a hash map. You store all the you categorize all the 3-letter words together, all the 4-letter words together, all the 5-letter words. Key, 3, value, list of strings, right? Where it's the list of all the letters that are all the words that are 3 letters long. 4 is the key, and the value is a list of all the words, right, that are 4 letters long. That's the other use of a hash map, categorization, right? So we gather all these into a list, right? And we lie, telling them, okay, I've got my hidden word. Okay? Now what happens is the player will start by guessing E. And that's a pretty strong guess that you'll see for most people to start out with. They'll guess E because E is the most common letter in the English language, right? Although, as hopefully I pointed out to you at some point in the videos, did I mention that there's a novel that's been written that does not use the word E? Somebody wrote an entire novel, Gadsby, that does not use the letter E in it whatsoever. Because, I guess he had too much free time. I mean, this was before the internet was created, so Okay. So anyway, player guesses E. It's a sound strategy, and now we would have to reveal all the E's in our word. Okay? So what we do is that we basically compute all the possibilities that could occur from the player guessing E, right? So let's underline all the E's here. This has no E's. Team has an E in the second position, right? Look has no E's. Good has no E's. Eggs has an E in the first position. Echo has an E in the first position. And edge has an E in the first and the last position, right? So in other words, if I had only one word that I was working with, like I should be, and edge was my word. If they guessed E, I'd be revealing E blank blank E. So what we do is that we then categorize all these words in our word list into word families. In other words, this is what would be revealed if I went with this family as a guess, right? So in other words, if I decided that the words I wanted to stick with were this, look, or good, they would see blank 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 because if this, look, or good was my hidden word, what would be revealed? Nothing. Nothing would be revealed because none of them have E's. Make sense to everybody? However, if my word was eggs or echo, the player would be seeing E blank blank blank, right? So those are in the same family because they both would have one E revealed at the beginning. So it's not just that one E would be revealed, but it's also in the same position. Okay, the player would see blank E blank blank if the hidden word was team, and then they would see blank EE blank if they chose edge. So we split all this family into multiple lists, divided by the word families. We use a hash map to do this, right? Where basically the key is our map, is the family, and the value is the list of all the words that belong in this family. So what we have to do then is now we have to choose one of these families and present it to the player as the reality, right? And the reason is that basically we are committing to pretending this is our group of hidden words, right? I can't say I'm going to pretend like you chose this looking good and then at the end say, oh, I was thinking of echo, right? I can't tell the user, oh, there's no E's in here, right? And then they come back later, and then I come back later and say, "Oh, I'm sorry, the word I was thinking of was echo." They're gonna call shenanigans on us, okay? Right? I can't tell them that the word doesn't have E, and then say later it has an E in it, right? We make it pretty obvious that at best they'll assume that it's broken, and at worst they'll call you a cheater, okay? So what we have to do is that we have to commit to this, and basically we use the word family as our new word list, right? So if we go with this group, we're going to be committing to basically the word that we're thinking of is going to be either this, look, or good. Okay? So what word family do we go with? The family, that's a strategy. That's something that I would say you should totally choose as your own strategy, but you're more than welcome to use the strategy that I use because it's one of the easiest ones, which is you just simply go with the biggest word family because honestly, we as human beings love to avoid commitment, right? So go with the biggest word family because that means that we don't have to commit to a word anytime soon. So we choose this looking good as our word family. We reveal blank, 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 blank. Tell them they're wrong, deduct a wrong guess from them, and say, okay, you had 5 guesses to begin with. Now you have 4 wrong guesses left, right? You've got this looking, and so now I say my words are this looking good. So now if they choose O as their next guess, unorthodox, then we split this up into word families. Right, this has no O's in it, so it goes into blank, 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 blank. Right, we completely rebuild our word families each time they make a guess, by the way, right? Each time we make a word family, it's a new. Each turn we make a new word, we split it up into word families, it's a completely new turn, or new word families. So this goes into the new word family that has no letters in it, while looking good, they go into the one with double O's in the middle. And because my strategy says I'm going to go with the biggest word family, I'm going to reveal blank OO blank, say great job, you got a correct guess, and I'll reveal the hitting goal O's and wait for the next guess, right? Okay. So here's the algorithm that you want to use. You want to read your dictionary.txt file, store all the and store it in the program at runtime. That's the stuff that's all the words that are in the dictionary. And I believe I give you a Scrabble dictionary for this one. Okay. Ask the user to choose the size of the hidden word they want to try to guess. If it's not a valid word size, so if they ask for a 50 bajillion, then just tell them there's no words 50 bajillion long, right? If they ask for something with 20 letters, then give them 20 letters if you have words with 20 letters, right? Next, ask them how many wrong guesses they'd like to have, right? Because you're a cruel person. So I generally find that that because I know how this game works, that if I go with 8 letters, if I say I have 8 letters, I can generally get the word in 8 guesses. But let them choose, because if I know you're using that strategy, I can actually force the computer to choose a word with enough strategy. All right. So then create your initial list of hidden words. And then play Hangman using our cheating algorithm. Print out the revealed words, the wrong guesses, and the remaining number of wrong guesses. Then get the user's new guess and be nice and ask them to re-enter it if it's a guess they've already made, right? So then, once they've made a guess, separate your list of hidden words into word families based on that input. Choose a word family using some strategy. Make that the new hidden word list. And if this reveals guesses to the user, reveal letters. Otherwise, they lose a wrong guess. Keep going until if all the letters are revealed, unlikely, the player wins. If they run out of wrong guesses, then you mock them, okay, make them feel very sad for being a student at a university, right, and unable to win a children's elementary school game, right? And what you want to do is that you want to choose a word from your remaining word list. Just choose it at random and pretend that was the word you had all along. Okay? And then ask them if they want to subject themselves to this torture again. Okay? So I don't really care what data structures you do end up using, but I highly recommend using sets and hash maps, right? Hash sets and hash maps in this one, because that will make it a lot easier for you to do. You'll be using lists, probably, maps, and sets. And, you'll want to remove it when you play for real, but I find for debugging purposes, it's very useful if you print out the size or the contents of your hidden word list at each turn, so you can see it shrinking down, right? Obviously, you want to remove that when you're subjecting your roommate to this game. But that will let you know that your program is cheating properly, right? Okay. So that is the program that. So that is my summary of sets and maps and the and what you're going to be doing for the next couple weeks. So this will be due after your exam on Friday. Next week I won't stop my lectures, but it's going to be a much easier series of lectures. They're kind of a break from this one, and that's my sorting lab. And I may or may not give you homework on that one. I might actually decide to skip homework because giving you homework on sorting because it's not actually too difficult. But sorting will be on your final exam. So, that just really depends on how far you guys get this week on this lab.